Hello everyone and welcome back. I hope you had a nice break and see that a lot of you are talking to each other, and we're very happy to see that, because it's of course one of the main goals of this conference that you should all mingle and network with each other so that this conference might lead to some future cooperations. Great, so with that I would like to introduce to you another of our Mobile Heights member companies, which we are very, very proud of here in Skåne, and that is NordAmps. And NordAmps is based here in Lund, actually, at the ID and Science Park. And NordAmps are experts in nanowire transistors designed for high-frequency wireless communication. And to present here, we have the CEO of NordAmps, Mr. Lars, who will tell us all about how to enable the move to above 100 gigahertz carrier frequency for 5G and 6G. Right? The stage is yours.
Okay, so I will give you the short story of NordAmps. NordAmps was formed some 5 years ago as a spin-out from Lund University in order to commercialize the vertical nanowire transistor technology that has been researched and developed at the university and at Lund for at least 15 years. And we are now offering the market the vertical nanowire transistor. The basic principle is quite simple. And you see to the left here, electron microphotograph of the nanowire devices roughly in the middle of the processing. And by growing the nanowires vertically on a silicon wafer, we form a vertical channel for the current, and enabling the formation of a gate metal that can be then wrapped around, I think I used a pointer, I have a more analog pointer. So it's actually, here you have a schematic view of how the device is working. The nanowire in the middle is actually then the channel for the current transport, and the beauty of having it growing vertically out from a silicon wafer is that you can then wrap the gate metallization around the channel, so you can control the current from all directions. And that gives you a higher gain. You can control it with the lower voltage, and that gives you a higher gain. And since we are then using a nanowire here, the growth mechanism enable us to choose material, not entirely freely, but we have chosen indium gallium arsenide because it has such a high electron mobility. So we actually get an electron transport here which is roughly ballistic. So this is the basic principle of how it works. There are numerous evolving areas and megatrends in society that are depending on increasing data communication rates. And this can be then provided, and the need is that you need millimeter wave frequency devices for that to happen. And we are focusing on 5G and 6G telecom application, partly because that's our heritage, but we are also in discussion with satellite communication, and we are part of a project together with IBM, Fraunhofer, and others in the EU constellation for quantum computing, where our devices are very well suited to read out the faint cubic signal from a deeply frozen quantum computer. And of course, due to the performance and characteristics of our devices, we can have a power-efficient application, and that means that we are also in the sustainability area. In order to deliver on the promised data transfer speed of transfer speed and to deliver on the promised data transfer speed of 5G and 6G, we have to go up in frequency to get access to the wider bandwidth that are available only at higher frequencies. So the general trend is now to go up in frequency for a lot of applications, but mainly for 5G and 6G. 5G is now commercialized at 28 and 39 gigahertz. And the next revision of the standard will means that we have to go up to 80 gigahertz. And for the backhaul channel, that means from the base station to the core network, we have to go up to the D band, around 150 and up to 170 gigahertz for 5G. And for 6G, we have to reach 300 gigahertz carrier frequency. That means that you need to have the cutoff frequency at least 3 times higher than that. And the underlying problem that is facing us today is that the standard CMOS technology is leveling off. For the digital application, this happened 10 years ago, so you can't really find a processor that is running at a higher clock frequency than 4 gigahertz or something like that. And for analog application, this happens at around 80 gigahertz. It's difficult to come above that with standard CMOS. And also the power consumption for all these base stations that has to be rolled out in order to cover for 5G and cover because the attenuation is much higher at higher frequency. You have to have many more base stations. That means that, and there's also MIMO and stuff like that consumes a lot more energy. So if nothing is done, this will be really a big problem for the operators. The main advantages for our technology is that, of course, that we can go to higher frequency and then reach higher bandwidth. But these devices are also more linear than traditional ones, and the low noise contribution is low because of the concept of the current transport. And we are compatible with conventional silicon technology because our thermal budget is reasonable and we don't destroy the CMOS that is already processed. And all of this above, that means that we can also have or enable a much lower power consumption, which is really an important aspect. To the right here, you see an illustration of the frequency characteristic of our devices. On the y-axis, you have power gain, and on the x-axis, you have a log scale of frequency. And as you know, per definition, the cutoff frequency is defined as when the gain is 1, that is in dB, it's 0. So this is the cutoff frequency of an earlier generation of our devices at 140 gigahertz. The next generation that is now in the fab is 400, and we are forecasting the next generation at 700, and then we are planning for 1 terahertz. So what is it actually that we are going to market with? Yeah, it's a product, and the product, one of the main aspects of the product is our design environment. That means our PDK. That's what you use for design circuits in our technology. And to the left here, you see the schematic view where you connect in a symbolic way the different transistors. To the right, you see the layout view where you can see how it will turn out on the chip later on. And this is then you can identify the finger structure here of a transistor. And if you look really careful, you can see the yellow dots of the standing vertical nanowires out from the screen. And so this is actually a PA, power amplifier, that we have designed, and just to show how well it would work. And then we can then tape out a GDS2 file from this. But before you do that, you want to extract parasitic components and feed that back to the simulator and do an iteration and see that you get a more precise estimate of the performance. And we can also give you a tool for estimating the circuit performance spread in statistical means, and that is based, of course, on the process spread. We have actually got market validation from a number of collaboration partners that we have collaborated with. A global 5G infrastructure provider has evaluated our technology and used that for swapping devices, our devices against the technology that they were using at the time. That was for 39 gigahertz, and even at that low frequency, they could show excellent results, both in terms of noise and gain. And now we are in collaboration with Cadence, Ericsson, and Lund University in a bigger project to develop a low-noise amplifier for 5G and 6G application. And this is a 2-year project. We have run it for soon 1 year. I'm very fortunate to work with a really competent and experienced team. I think more or less all of them are here today, so take the chance to talk to them and discuss what we are doing. Lars-Erik Wernersson, you will meet in a few minutes here on stage. Yeah, exactly. Erik Lynred, I don't think he is here yet. But then we have Tobias, he's our expert in circuit design. Simon is the designer behind our PDK and our design environment. Yeah, I can see you over there. Yeah. And we have Aline. She's our expert in finite element simulation, giving the understanding of how the transistors are really working and so on. And then quite recently we have recruited Sven Mattisson to the team as well. So he's part-time employed. Since he is now retired from Ericsson, he decided to join this enterprise. And we're very happy. No, he is unfortunate not. He is out traveling.
I think we have to mention one thing about Sven Mattisson.
Yes, of course. I mean, you can mention a lot of things. He is really an expert in wireless communication. He's actually one of the 2 inventors of the Bluetooth technology.
Thank you.
So we are very happy to have him on board. He knows everything about wireless communication. So we are that's comforting for us. And to summarize, we have the solution for enabling the move to higher frequency, for instance, for 5G and 6G, so that the operators can deliver on the promise of 5G and 6G for data communication rates. And the concept has been validated experimentally in the university lab. And the device structure and the realization has been protected by a number of patents. And we are now happy to engage with customers and both end customers and foundry customers like ST maybe, and Global Foundries and others. Yeah,
we have another meeting. Why?
We will see. We haven't settled that yet. But anyhow, this is really a very exciting journey. And as you mentioned earlier on, semiconductor is really fun and inspiring. So I welcome all the brilliant students to come and talk to us before you move to some other place in Europe.
Thank you very much,
okay,
Lars.
Thank you.
Thank you. So if we have one quick question from the audience, we could take that now. Otherwise, you will have plenty of time during lunch. Yes, we have one question. Please present yourself.
Yes, thank you. I'm Tony Mandron from Minalogic. What is the typical size of your nanowire and what kind of node you can reach?
They are roughly 30 nanometer in diameter and between 100 nanometer and 400 nanometer long. That depends on the application.
Okay. Thank you very much, Lars.
So very tiny.
Thank you.
Thank you.
Thank you.